Welcome back to Physics 141 Online. Here's an example of a collision where we are told in the problem statement that we have an elastic collision, and we'll use that information to solve the problem. A ball of mass m moves along the positive x direction with speed v0, and it makes a head-on elastic collision with a second ball of mass 2m moving along the minus x direction with a speed v0. Find the velocity of each mass after the collision. Remember that head-on, there's information here that head-on means it's a one-dimensional collision. Elastic, of course, means that both momentum and the total kinetic energy of the system are conserved. So let's start, as always, with a sketch. All right, the positive x direction we will take to be this way, the I hat direction, like that. So we have a mass m moving with a speed v0 along the positive x direction, and there's a mass 2m heading toward it with a speed also v0. So that's the situation before they collide. And after they collide, we're not told anything. We don't know for sure. And so we just have to make some assumptions. So I'm going to assume that the mass, little m, rebounds backwards. I think that kind of makes sense. We would expect that because the mass 2m is moving at the same speed, but it's a larger mass. But I don't know what the speed is, so I'll just call this v1 final. Now, mass 2m, I don't know which way it's moving, so I'm going to guess. And I might be right, I might be wrong. So I'm just going to guess it's going to continue moving the same direction it started. So it will have, this is mass 2m, it will have a speed v2f. And if I'm wrong about either one of these, what will happen is I'll solve for those two quantities, and I might get a minus sign. And if I got a minus sign, it will simply mean my picture was wrong. So what we're going to do is solve for v1 final and v2 final. And first, we're going to use the momentum conservation equation. And I won't write it out with the summation, but I will just write down the terms that give me the total momentum before the collision and then set it equal to the total momentum after the collision. So before the collision we have, right, we've got m v0 in the positive I hat direction. That's for the left hand mass. For the second one, we've got 2m v0, but it's in the negative I hat direction. And that's what we have initially. After the collision, we've got m v1f in the negative I hat direction, again minus 2m, plus 2m v2f in the negative I hat direction. So I could put the minus sign out in front if I wanted, but this way you can see that each term has a magnitude, that's a mass times a speed, and then the direction of the vector is indicated with the plus or the minus I hat. So what I can do is simplify this, because if I factor out the I hat, what I really have here is I've got m v0, right, minus 2m v0 times the I hat unit vector, and on the right hand side I will have a negative m v1f minus 2m v2f, right, times the I hat unit vector. So if those two are equal, then the terms in parentheses must be equal. So on the left hand side I have negative m v0, and on the right hand side I just have negative m v1f minus 2m v2f. Okay, so what can I do to simplify this? Well, let's just go ahead and solve for v0, and I can get this because if I divide both sides by m, the m terms cancel out. If I multiply both sides by minus 1, then all those minuses become pluses. So I'm left with v0 equals v1f, right, plus v2f. And I'll call that equation number 1. We'll use that in just a minute. I can't use this directly to solve for either one of my unknowns, v1f or v2f, because they're both in that equation. So I need more information. I need one more equation. And let me just remind you that in a problem like this, when we solve for these two unknown velocities, we're going to solve for them in terms of the given quantities, and particularly here in terms of v0. So that's from momentum conservation. Now let's write down what we get from kinetic energy conservation. That's easy. 1/2 m v0 squared is the kinetic energy of the first mass. Then we have 1/2 times 2m v0 squared. That's the second mass. Remember that it's positive because kinetic energy is always positive, and it's got the mass 2m in there. All right, be careful that you don't forget things like that. So afterwards we have 1/2 m v1 final squared plus 1/2 2m v2 final squared. All right, and that's pretty simple. Let's see, what can I do with this? Well, I can multiply both sides by 2 right away, and so the 1/2 terms will all disappear. And then I can combine these first two terms because it's mv0 squared plus 2m v0 squared. That's 3m v0 squared on the left-hand side equals, now the first term on the right, what do they both have in common? They have an m in common, so I'll factor out an m. m times v1 final squared plus, here I would have just a 2 v2 final squared. So last thing I can do is divide both sides by m, and I end up with this equation here that says 3 v0 squared equals v1 final squared plus 2 v2 final squared. And I'll call this equation number 2. I've got these two equations to work with. And that means I should be able to combine these two equations in a clever way and solve for the two unknowns, because when you have two equations and two unknowns, you basically know that you can solve it. Sometimes the algebra is a little messy, but you know you can do it. So let's, in equation number 1, I'll show you one way to do this. There's more than one way, but one straightforward way is to solve for one of the unknowns in equation number 1 and plug it into equation number 2. And the reason I want to do that is equation number 2 has the squares. So I want to solve for one of the terms without having to take a square root. Then I'll be able to plug it into the second one. So my strategy first will be to solve for VF in equation 1. Solve for V1F in equation 1. And that gives me V1F equals V0 minus V2F. Well, now since I want to plug that in here, I'm going to have to square it, so I might as well now do the squaring. V1F squared, right, which will just be this term multiplied by itself. V0 minus 2F times V0 minus 2F. Well, that's going to be not too hard. I do have to remember a little bit of algebra to be able to FOIL those out, but this will give me V0 squared minus what have I forgotten? Look up here. I made a mistake in my equation number 1. It's a good thing I caught this now. I forgot this factor of 2. So my equation number 1 should properly read V0 equals V1 final plus 2 V2 final. So that's all I need to add here. Now, I didn't make that mistake in equation number 2. Equation number 2 is okay. I remembered the factor of 2 there. But now, okay, this actually should be V1 final is V0 minus 2 V2 final. So that 2 goes in each of these places when we square V1 final. So this becomes V0 squared minus 4 V0 V2 final plus 4 V2 final squared. All right, and that is what I'm going to plug into equation 2. So I'm going to rewrite equation 2 and plug this guy in right up here. So equation 2 becomes 3v0 squared equals, and now this whole term here goes in there. I'll just recopy it. v0 squared, right, minus 4v0 v2 final. Make my 4 a little bit better, plus 4 v2 final squared. All right? And there's one more term, plus 2 v2 final squared. So I can consolidate this a little bit. These two terms give me 6 v2 final squared. And then I can get everything on the left-hand side of the equation, because I'm going to set this up where everything on the left-hand side equals 0 on the right-hand side. So the 3v0 squared and the v0 squared becomes 2 v0 squared. This term then becomes plus 4 v0 v2 final. And then this becomes minus 6 v2 final squared equals 0. All right, and I've got one equation with one unknown. The unknown is v2 final. And this is clearly a quadratic equation. So I'm going to have to work a little bit to solve it. But let's first, before we have to use the quadratic formula, let's make some space up here and see if this equation factors. Because if it does, that's going to be much easier than using the quadratic formula. So let's check it out and see. I'll clear some space by getting rid of the momentum conservation equation. All right, so what happens? Well, this equation down here then, I first can divide both sides by 2. And that will give me v0 squared plus 2 v0 v2 final minus 3 v2 final squared equals 0. And sure enough, this actually does factor. It's what we get when we take v0 plus 3 v2 final times v0 minus v2 final. And you can check that to make sure, but it actually does factor that way. And the nice thing about that is that it allows us to look at the two possible solutions and consider which one makes physical sense. Because in most of these problems, you'll only get one unique answer that makes sense. But you have to check both of them out that come from this kind of a quadratic equation. So let's look at them one at a time. You'll remember that if the product of two terms is equal to 0, then either one or the other, or perhaps both of them, could be equal to 0. So let's look at the two possibilities. A, the first possibility, is if the first term is equal to 0, right? v0 plus 3 v2 final equals 0. And if that's the case, then that would be v2 final is equal to negative v0 over 3. The minus sign would just mean that my picture was wrong, that I guessed the wrong direction, and that the v2 final vector actually should point to the right. But that looks like a reasonable answer. Let's look at the second possibility, B. That would say that v0 minus v2f is equal to 0, or that v2f is equal to v0. Now let's look at that for a second. Look at the picture. If v2f is equal to v0, that would be the same velocity as that mass had initially. That doesn't make sense. Right? That would be like these two objects not even colliding at all. So this would be the no collision solution, as if they were moving parallel but never actually collided. And so as a result, that's not a physically meaningful solution. And so the very first one that we got is the one that makes sense. So all I have to do now to finish the problem is solve for v1 final using equation 1. So from equation 1, actually we've already done that down here. We've got an expression for v1 final. v1 final equals v0 minus 2 v2 final, and I've got to plug in with the minus sign what I got for v2 final. So this becomes v0 plus 2/3 v0, then, which is just, what is that, 5/3 v0? Right, 5/3 v0. All right, so we've got the two velocities, or we've actually got the two speeds, and in order to make the answer completely clear, it's probably a good idea to then write down what you get for V1 final and for V2 final, indicating the directions. And so that's easy enough to do, right? The answer then is that V1 final, right, I'll write it as a vector, is equal to 5/3 V0, and the picture for V1 final had it going in the negative I hat direction, and so that's correct. I got, for the magnitude, I got a positive answer, which means it agrees with the sketch. V2 final, then, the only difference here is I had it in the sketch in the negative direction, but I got a negative answer for the magnitude, so that actually means that V2 final is V0/3 in the positive I hat direction. Okay, so all of my equations were consistent with the sketch, but the fact that I got a minus sign means that the direction was wrong. So that's how to do an analysis of an elastic collision. I hope that'll help you on those homework problems, and I will see you in class.